This video is going to really cover one page in the course packet, and then it's going to do four problems from Siegel. These are problems 28 through 31 in Chapter 5. The topic of this page is rescaling data and some formulas that allow us to understand how rescaling affects means, standard deviations, and other statistics. Let me give you a little bit of context on this topic. This is probably one of the most important topics in probability theory. If you were to take a proper course in probability theory, these formulas would be sort of the tools that you would use on a daily basis. They're really indispensable. Their utility is a bit less obvious if all you're doing is analyzing data, but because they have such importance, and I'm going to be using them to justify certain results going forward in the course. So it's students find it a little bit abstract, but they're really useful and important. Okay. So what do I mean by rescaling? Let's say that I've observed a bunch of data. So I have n observations. Very often I want to do something to those observations. Maybe I want to change the units. So a rescaled version is just any linear transformation of the x's. So let me give you a couple examples of this. First off, changing degrees Celsius to degrees Fahrenheit. So I'm just changing units. Or if I'm going from US dollars to euros, that would just be a linear transformation because I'm multiplying by some constant. There are other examples that we're going to encounter. For example, if you go from the number of yeses to the percentage of yeses, you're really just doing a linear transformation, since to get from the number of yeses to the percentage of yeses, you're dividing by some constant n. All right, so there's another example of a linear transformation. So these things will be all around us. All right, so here's the result. Let's say that the mean of these x's, so notice I have a census here, is mu sub x, and the standard deviation is sigma sub x. Then if I do this transformation, the mean of y is just the same transformation of the mean of x. Okay, so instead of me having to recompute every new y value and then find the mean of it, I can just take the mean of x if I know that and drop it into this formula. Now, when it comes to the standard deviation, things get a little bit easier. The standard deviation of y is just take the multiplicative constant a times the standard deviation of x. Now, you got to get rid of the sign of that multiplicative constant, and that's what the absolute value does for us. Now, let's do a little example, yet another illustration of where linear combinations creep up on us. So, we make widgets. Our fixed costs are $10,000 a month, and then the marginal cost of the materials to make a single widget is $10. Okay, so for every additional widget that we make, our costs will increase by 10 bucks. The price of a widget is $20. Okay, so it looks like materials, double the cost of materials is the price. So on average, we sell 1,200 widgets per month with a standard deviation of 1,500 widgets. Compute the mean profit per month and its standard deviation. So let's say that x is going to be the number of widgets that we sell in a month. Then let's come up with an algebraic expression that relates the number of widgets we make to the profit. So what is it? Well, we make $20 less the marginal cost times the number of widgets, and then you got to subtract off the fixed costs. So our profit then is going to be just 10 times the number of widgets we make less 10,000. So then if the mean of x is 1200 and the standard deviation is 1500, the mean profit, just drop 1200 right into that linear combination formula. Mean profit is 2000, standard deviation is going to be, well, 1500. So 10 is that multiplicative constant. There is no sign to drop. All right, we're going to get the Sketchbook Express up.